Hello students. Today we will discuss Fourier transform. That is our it comes under second chapter. Okay. So before that we have discussed about Fourier series, right? So we have discussed Fourier series right now. So we are going to discuss Fourier transform, right? So why we need that Fourier transform? That is the first question, right? Why we need that Fourier transform? Because we are our original signal is a time domain signal, right? So you can take any example, any signal, right? Our original signal is time domain signal. Okay, wow. So in our time domain signal, we can't analyze the signal accurately. For example, I want to measure the amplitude at the particular time period, right? So it is very difficult to analyze the signal within the time domain. So that's why we are converting time domain signal to frequency domain. Okay, so in order to convert time domain signal to frequency domain, we have one method. That one is the Fourier transform. Okay, the transformation means we are converting time domain signal to frequency domain by using a frequency transformation method. Okay, so why we are converting? What is the advantage of converting time domain signal to frequency domain? So we can easily analyze the signal if it is in frequency domain. At what frequency the amplitude is there, we can easily measure. Okay, but in time domain it is very difficult to measure the amplitude at a particular frequency. So that's why we are converting time domain signal to frequency domain. Okay, so we can easily measure the amplitude of a particular signal at a particular frequency. Okay, so we will take one example. Okay, you know that already what is a periodic signal and a periodic signal, right? So periodic signal means what? Periodic signal, if the signal repeats, one second, if the signal repeats after the fundamental time period, such type of signal we call that one as a periodic signal. If the signal does not repeat, okay, after the fundamental time period, such type of signal we call that one as a periodic signal. We will take another example. That one is usually I will use that sine wave representation. Today we will see that square wave. Okay, see here, this is square wave for the period for the fundamental time period t. Okay, see here, this square wave repeats after the fundamental time period. Okay, such type of signal we call that one as periodic. If it does not repeat, then such type of signal we call that one as a periodic signal. You know very well these things. Okay, so we will see that spectrum, frequency spectrum, right? So I said before, Fourier transform is used to convert time domain signal to frequency domain, because we can easily analyze the signal. For example, we can easily measure the amplitude at a particular frequency. Okay, so that's why we are converting time domain signal to frequency domain. I will give another example. Okay, I will give another example why we are converting that time domain to frequency domain. Okay, see here, um, this is 1 hertz sinusoidal signal. Okay, we will take 2 hertz sinusoidal signal. Okay, similarly we will take 4 hertz sinusoidal signal. Okay, these are the three different types of signal with different frequencies. Okay, so here my main goal is, main objective is, I have to determine at a particular frequency what is the amplitude. Okay, or at a particular time period what is the amplitude. Okay, for example, I have to determine, okay, time, at the time 2 second what is the amplitude. Okay, at a time 2 second, so what is the amplitude. Okay, for both 1 hertz, 2 hertz, and this is a 2 hertz, this one is a 4 hertz. Okay, x-axis is t. Okay, y-axis is amplitude. Okay, so usually during reconstructing our signal, okay, while receiving the signal, okay, while receiving the signal, usually we will get at the receiver, it will combines all three signals. Okay, we will get like this: 1 hertz, okay, 2 hertz, then 3 hertz, like that. Okay, here in this time it is very difficult to determine. Okay, x-axis is time, unit is second, y-axis is amplitude. If it is in voltage, unit is volt. Okay, so here I have to find out what is the amplitude at a particular, I mean at t is equal to 2 second. Okay, see here in this graph, it is very difficult to determine the amplitude at a particular time period. Okay, see here, for example, if it is t is equal to, if t is equal to 2 second means, okay, it will come here. Okay, so it is overlapped. Okay, it is whether the frequency that 2 volt is belongs to 1 volt, sorry, 1 hertz, or 2 hertz, or 4 hertz. It is very difficult to analyze. Okay, for example, if I am converting time domain signal to frequency domain, see the frequency spectrum. So I will get, first, this is 0 hertz. This is a frequency. X-axis is frequency. Okay, y-axis is amplitude. Okay, for 1 hertz, I will get some amplitude. Okay, this is 1 hertz. In 1 hertz, the amplitude is 2 volt. Okay, at 2 hertz, right? So at 2 hertz, the amplitude is 2 volt. At 3 hertz, the amplitude is 2 volt. Okay, this is the frequency spectrum. So we know these things. So just it looks like our continuous time signal is converted into discrete time signal, right? So similarly, the same thing only. Here we are converting time domain signal to frequency domain signal. We can also call this one as frequency spectrum. Okay, this is a spectrum, frequency spectrum. X-axis is frequency, y-axis is amplitude. See here, so I can easily analyze the signal. 1 hertz signal, I am getting 2 volt, right? 2 hertz signal, 3 hertz signal, there is no overlap as like in the time domain signals. Okay, this is the advantage why we are converting time domain signal to frequency domain. Okay, and one more thing, I will take another example. Okay, just I will explain in detail. Okay, um, see here, I will take sync function. You know very well what is that sync function, right? So we are writing sync function like this. Okay, so sync function. Okay, wow. So now I am converting this continuous time signal to discrete time signal. Okay, wow. Or we can also call this one as frequency spectrum. Okay, so I will get the frequency spectrum like this. Okay, so okay, wow. So here, see here, this is the frequency spectrum. F, okay, x-axis is F. This one is an amplitude. Okay, this is a sync function, right? Frequency spectrum of sync function. Okay, so this we call this one as a frequency spectrum. These are the samples. Okay, these are the samples. The first thing is the amplitude at omega is equal to 0. We can also take, instead of frequency, we can also take that one as omega. Okay, omega representation is radian per second unit. Frequency, we are representing the unit is hertz. Okay, usually we will take either frequency or omega. Okay, if omega is equal to 0, right, if omega is equal to, at omega is equal to 0, the amplitude is 2 by t. What is the t? T is the fundamental period. If t is equal to 3, then we will represent as a 2 by 3. Okay, wow. Similarly, the fundamental frequency, we know that equation. How we are determining that fundamental frequency? T is the fundamental time period. Omega naught is the fundamental frequency. How we are determining that fundamental frequency? Omega naught is equal to 2 pi by t, right? So T is the fundamental time period. Omega naught is the fundamental frequency. Then how to determine the spacing between the two samples? How we are determining the spacing between the two samples? By using this equation, right? Delta omega. Delta omega is the spacing between the two samples, or the difference between the two frequency, right? So this we call this one as a delta omega. This is the space between the two samples. Okay, the difference between the two frequency. Okay, so the equation is, okay, the same equation what we have used that in order to determine the fundamental frequency, the same frequency 2 pi by t. T is the fundamental time period. If t is equal to 3, it becomes 2 pi by 3. Okay, then another important point is, right, so zero crossing. Okay, first zero, where that zero crossing occur. What is that zero crossing? So if the point is here, if the point is, for example, that sample is here, right? So if the sample is here, the amplitude is 0. Okay, if the sample is here, okay, so then we call that one as zero crossing. Okay, see, we call that one as zero crossing. I will tell you in detail. Okay, what is that zero crossing? Which means the amplitude is 0 at a particular frequency. The amplitude is 0, so we call that one as zero crossing. Okay, we call this one as zero crossing. Okay, the first zero crossing occur at n is equal to um, n is equal to t by 2. Okay, actually, in order to determine the zero crossing, we are using this equation. Please note down these equations. Okay, so fundamental frequency. Okay, determine the space between the two samples. Okay, or frequency difference. Okay, this is the we can use in order to determine the zero crossing frequency. We are using this equation in generally. Okay, in generally we are using this. N is equal to small n is equal to t by 2. And also the first zero crossing occur at, okay, at pi. Okay, first zero crossing usually occur at pi. Okay, these are the basic concept related to the frequency spectrum. Okay, we will see what happens if the fundamental time period increases or decreases with respect to the frequency spectrum. Okay, see here, I will take that same sync function. Okay, see here, um, this is frequency spectrum. Okay, this is frequency spectrum of sync function. Okay, n, right? So this is n is the number of samples, t is the fundamental time period is equal to 3. Okay, this is the space between the two samples. Okay, we are calculating by using 2 pi by t. Okay, the first sample, the first zero crossing frequency, first zero crossing frequency occur at n divided by t by 2. Generally, it occurs at pi. Okay, wow. So we will see, this is for t is equal to 3. Okay, we will calculate, we will draw the frequency spectrum for t is equal to 5. Okay, see here, this is n x-axis, this is y-axis amplitude. Okay, so here t is equal to 5 and also the number of samples is increased. Okay, in the sinc function. Okay, wow. See here. Okay, so here for t is equal to 5, the number of sample is increased up to 5. For initially, the number of sample is 3. For fundamental time period is 3 second. So for t is equal to 5 second, okay, so the number of samples are increased. Similarly, if t is equal to 10 means the number of samples are increased up to 10. 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the number of samples are increased for t is equal to 10. Similarly, for t is equal to 20. So what happens if the number of samples are increased? Okay, what happens if the number of samples are increased? First of all, first of all, the amplitude will get reduced. So I will draw a neat diagram. I will show that how it will decrease. Okay, see here. So initially the amplitude is 0.7. We will take that amplitude. Okay, for t is equal to for t is equal to 3, the amplitude is maximum amplitude. I am taking maximum amplitude. Okay, 0.7. Okay, I will increase the number of samples. Okay, if t is increased to 5. Okay, the number of samples are the number of samples are increases. Okay, 3, 4, 5. Okay, then amplitude will get decreases. Okay, so again, if t is equal to 10 means the number of samples will increase, but the amplitude get decreases. Okay, so the drawback is, so the amplitude of the signal will get reduced when the number of sample increases. Okay, then spacing between the components, right? If the number of samples increases in one period, for example, if it is one period, I will take one sinusoidal signal. Okay, this is one period. Okay, t. Okay, this is t. So I am increasing that number of samples within the fundamental time period. Okay, see here, I will increase number abruptly. I will increase. Okay, so what happens here? The spacing between the two samples is very high, right? Very large. But here, as the number of samples increased within the single period, within the fundamental time period, so the gap between the two sample get reduced. Okay, va? And also amplitude get decreases. Okay, and also number of zero crossing, right? Where will occur generally? The zero crossing occur at when amplitude is 0. So the number of zero crossing will get increases. Okay, and also the change, it changes if the samples are increases. It changes the shape of the sinusoidal signal. Okay, these are the some of the basic concept about frequency spectrum. The main concept is why we are using that frequency Fourier transform in order to convert time domain signal to frequency domain, in order to analyze the signal easily. Okay, so with accurately we are converting time domain signal to frequency domain. Okay, that is the main concept. Okay, we will solve one problem. We will see in the next video. Thank you very much. I think you will get you will understand this concept. Thank you.